Okay, thank you very much. It's a pleasure to be here. Thank you so much to both the workshop organizers and the semester program organizers. Really lovely to be here. So I want to talk today about topological Hochschild homology, Witt vectors, and equivariance. And I'm aiming to talk about a project that's joint with Anna Marie Bowman, Cameron Kerlewski, Sarah Peterson, and Lucy Yang. But I'm going to take my time getting to our actual project so that I can do some background and have this be a little bit of a sort of gentle introduction since it's Friday and we're tired and it's lunchtime. So we're going to talk about THH, Witt vectors, and equivariance, as I said. And a lot of the objects I'm going to use throughout my talk we've sort of seen throughout the week already, so hopefully there will be some familiar players. And I am going to reintroduce some things we've already talked about just so I can focus on different aspects that I'm interested in. Okay, so the motivation from this project comes out of trace methods in algebraic K-theory. So I want to start by saying a little bit about that. So trace methods in algebraic K-theory. So we've heard about algebraic K-theory already this week, and one of the takeaways from, for instance, Mona's talks is that algebraic K-theory is this really interesting invariant of rings that connects to different areas of mathematics. So we heard from Mona about how K-theory connects, for instance, to diffeomorphisms of manifolds through things like the S-cobordism theorem. So algebraic K-theory is an invariant of rings that we're very interested in computing, but it's notoriously difficult to compute. So trace methods is an approach to try to compute algebraic K-theory. And I'm going to tell you about the approach, but the idea that you should keep in mind is simple enough. So the idea is just K-theory is hard to compute. So let's try to approximate it. So we're going to approximate K-theory by more computable invariants. So if you get lost in the trace methods discussion, you can always come back to that this is our goal. We're trying to approximate K-theory by things that we have a better chance of being able to get a handle on. Okay, so how does trace methods start? Well, the very beginning of trace methods is that if I have my algebraic K-theory of a ring, it turns out that there's a map called the Dennis trace that relates algebraic K-theory to a classical invariant of rings from homological algebra called Hochschild homology. So we have this trace map from algebraic K-theory to Hochschild homology. Okay, the plus minus on the Dennis trace is that I was trying to approximate K-theory by things that are more computable, and Hochschild homology is definitely way more computable. So we win. Except the minus is that this is not a very good approximation, right? So Hochschild homology, we've lost a ton of information in doing this map. So in kind of the late 80s, early 90s, the idea emerged that maybe the problem here is partly that this is defined purely in homological algebra. It's really a purely algebraic thing. Whereas this is defined as the homotopy groups of some space or spectrum. So maybe if I wanted more information, maybe I really wanted a topological version of this thing on the right as opposed to this purely algebraic version. Okay, we know such a thing exists. We've heard about it from both Jeremy and Emanuele already this week, but let me remind you that there is this notion of topological Hochschild homology. And this was first constructed by Bachstedt. Okay, so I'm going to talk a lot about THH today, so I am going to redefine it, even though we've heard briefly about THH already, but I want to sort of tell you a little bit more about what it is. And so topological Hochschild homology is an invariant of a ring spectrum. So I want to think about a ring, but now in topology. So I'm going to let R be a ring spectrum. And we can define THH via something called the cyclic bar construction. So B cyc R be the cyclic bar construction. Okay, what is this thing? It's going to be a simplicial object, a simplicial spectrum. And how do we define it? Well, I'm going to tell you what the Q simplices are. So at level Q, I'm going to take my ring spectrum and smash it with itself Q plus 1 times. So let's draw a picture. So at level 0, I've got R, then R smash R, then R smash R smash R, etc. And if this is a simplicial thing, I need to also tell you what are the face and degeneracy maps relating these different levels. So for instance, for my face maps, I should have 2 maps here, I should have 3 maps here, and so on. I have degeneracies going in the opposite direction. And what do those maps do? Well, if I really forced you to write down some maps from 3 copies of R to 2 copies of R, what's a natural thing to do? Well, it's a ring spectrum, so I have a multiplication. So one natural thing to do is maybe I multiply the first 2 coordinates and then smash with the identity. That's this map. But why did I multiply the first 2 coordinates? Maybe I should have multiplied the last 2 coordinates. So I could have done identity smash mu. That's this map. Or a different thing that I could have done is I could have multiplied this coordinate and this coordinate, the first and third coordinates. So in other words, I could have wrapped that last coordinate around to the front and then multiplied. That's this map. Okay, and you can imagine how you generalize that to sort of form all my face maps in my cyclic bar construction. And I have degeneracies as well. They go in the opposite direction. And the degeneracies insert the unit in various places. I'll just say degeneracies insert the unit. Okay, I have this object. It's called the cyclic bar construction. This is a simplicial spectrum. And what is topological Hochschild homology? Well, one way of saying what topological Hochschild homology is it's the geometric realization of this cyclic bar construction. Okay, a side note, I told you Bokstad defined this, and then I wrote this, and if you go and you pick up Bokstad after class today, and then you look at it, you're gonna feel like I lied to you because it seems much more complicated. So Bokstad did this a long time ago, and Bokstad didn't have some of the nice things we have today, like a nice symmetric monoidal category of spectra with an associative smash product. So Bokstad did a lot of extra work to execute this idea, but this is certainly what's happening, underlying what Bokstad was doing. And now today this makes sense to say that THH is this cyclic bar construction. Okay, I was trying to approximate algebraic K-theory. So we could ask, how does this relate to K-theory? And it turns out that there's a topological version of that Dennis trace that relates algebraic K-theory to topological Hochschild homology. Oh, a notational note. A was a ring. Maybe I never even wrote that. Sorry, bad choices. A is a ring, and R here is a ring spectrum. So what do I mean when I say THH of A? Like, what does it mean to take THH of a ring when it's supposed to eat a ring spectrum? It's just notation. When you see people write THH of a ring, what they mean is THH of the Eilenberg-MacLean spectrum associated to that ring. So it's just shorthand for that. Okay, so this is a better approximation to algebraic K-theory than Hochschild homology was. So that's good news. But we can do yet better. So we're going to develop another approximation to algebraic K-theory called topological cyclic homology, which we've also already heard mentioned this week. But I want to tell you something more about THH before we can do that. So let's notice something about topological Hochschild homology. I defined this as a simplicial thing with these face and degeneracy maps, but there's actually another operator sort of floating around here. So we also have a cyclic operator. So I have a cyclic operator at each level, tau, from, my, I don't know. Okay, sorry. So it stays at the same, I know how to do that. Okay, R smash Q plus 1. I don't know, mind blank there for a second. Okay, so it stays at the same level. What does tau do? This rotates the last factor to the front. Okay, and so if you think about what that does in your picture, on level 1 here, that gives me an action of C2. On level 2, that gives me an action of C3, and so on. Have these cyclic group actions at each level. And it turns out you could check for yourself that this cyclic operator satisfies really nice relationships with the face and degeneracy maps. And it's an example of an object that's well understood called a cyclic object. So in particular, the reason we get this name is that our cyclic bar construction is not just a simplicial object, it's a cyclic object. And there's a whole theory of these cyclic objects. And one reason that we like them is that when you geometrically realize a cyclic object, you get an S1 action. So the geometric realization has an action of S1 by Kahn's theory of cyclic sets. Okay, so in particular, it means topological Hochschild homology has an action of the circle. And actually, we can construct it as an S1 spectrum. So THH of R is an S1 spectrum. Okay, so why do I mention that? So it turns out we're going to use that S1 action on topological Hochschild homology to define our next approximation to algebraic K-theory. So, topological cyclic homology. So Jeremy on Wednesday gave us a formula for topological cyclic homology. You might remember it as this equalizer formula. So there are two sort of main ways to think about the definition of topological cyclic homology, and the formula that Jeremy gave us on Wednesday is due to Nikolaus Scholze from very recently, 2018-ish. That's one way of defining topological cyclic homology. For the work I want to tell you about today, I'm actually going to tell you about the classical way of doing it, the older way, which is due to Bäckstedt, Chang, and Madsen. So there's two ways of doing this, and this is, so if you're like, this is not the formula, if it doesn't feel familiar to what you saw Jeremy do, that's because it's not. I'm doing a different definition of topological cyclic homology than he did the other day. Okay, so topological cyclic homology. I have my THH. It has an S1 action, and you know we had a lot of equivariant people here. So what do we like to do with group actions? One thing we like to do is take fixed points, right? So I could ask about fixed points under subgroups of S1. So I want to think about, let's look at THH, and I want to think about the CP to the K fixed points of topological Hochschild homology. Okay, that's a thing I could do. We're going to see why we want to do that in a minute, but this is a thing I could do. And then you might ask, like, how are those fixed points related to each other as the subgroup changes? Also a natural question to ask. And so I have a map induced by inclusion of fixed points, which I'll write as F. So this is a map from, say, the CP to the K fixed points to the CP to the K minus 1 fixed points. And this map is called the Frobenius. Okay, so I have a map like this. I'm going to draw a picture so we can keep track of our maps. So my situation here is I'm trying to understand algebraic K-theory. I had a map to topological Hochschild homology. That was the topological Dennis trace. And now I'm saying, well, I could look at fixed points of THH, like I could look at the CP fixed points, and I have inclusion of fixed points. I could keep going. I could look at the CP squared fixed points, etc. And it turns out that this topological Dennis trace map, it lifts through those fixed points. So I have a diagram that looks like this. There's also a second map. So there's a second map, which is called the restriction. And it's also a map from the CP to the K fixed points of THH to the CP to the K minus 1 fixed points of THH. And with the Frobenius, there was like this nice one-sentence thing to say. It's inclusion of fixed points. The restriction is more complicated. So the restriction, there's not a nice one-sentence summary other than to say that, you know, this Frobenius, this is something, it wasn't really special about THH, right? I could have done something like that for any S1 spectrum. I could take these fixed points and include them. The restriction really is something about THH. It's about the fact that THH is what's called a cyclotomic spectrum. So uses that THH is a cyclotomic spectrum. I'm not going to define what that is. That's a big topic for a different day. But that's something about the S1 action on THH. But it's important to note that we need that here. We need it to be cyclotomic to define TC. Okay, but THH is cyclotomic, so I get this second map. It goes here, restriction, restriction. And then what is the definition of topological cyclic homology? So this is Bäckstedt, Chang, Madsen's definition. They said that the topological cyclic homology of A is the limit over these restriction and Frobenius maps of these fixed points of THH. So in other words, in my picture, TC goes up here. So topological cyclic homology lives up here. And further, what Bogstad-Chang-Madsen proved is that this topological Dennis trace map lifts all the way to TC. So this is called the cyclotomic trace. Okay, so let me write that down. So we've got a trace map from algebraic K-theory to topological cyclic homology, which is called the cyclotomic trace. And that's, again, Bogstad-Chang-Madsen. Okay, so, good. So the thing that makes trace methods go, that is that this cyclotomic trace map is often close to an equivalence. So the thing that makes trace methods work is that TC is a good approximation to K-theory. And that's vague, but of course the results are not vague. There are a lot of different, very specific theorems about this. One of the classical ones is the Dundas-Goodwillie-McCarthy theorem. So Dundas, Goodwillie-McCarthy. But there are many others, for instance, results of Geiser-Hesselholt, or more recently of Clausen-Matthew Morrow, that tell us about this comparison between algebraic K-theory and topological cyclic homology. But for the purposes of today, you should just think, well, really, I just want to compute TC. If I can compute TC, hopefully I have some comparison map allowing me to recover algebraic K-theory. Okay, but this method, the goal was to approximate K-theory by things that are more computable, right? So I've argued that this is a good approximation, but is it computable, right? This is only a good strategy if we can compute TC. So what is the strategy of many K-theory calculations these days? Well, if I want to compute algebraic K-theory, what I've just said is really I want to compute topological cyclic homology. And if I want to compute topological cyclic homology, I claim that we need to do some equivariant calculations. Now, which equivariant calculations you have to do and how equivariant those calculations are depend on whether you use a Bogstad-Chang-Madsen approach or whether you use a Nikolaus-Schulze approach. But either way, we're still in this same idea. And so we're talking Bogstad-Chang-Madsen today, and so what equivariant calculations do I need to do? Well, I need to compute those fixed points of THH, homotopy groups of the fixed points of THH. These come up so much and play such an important role that they get their own special name. And Emanuele mentioned it briefly on Monday, that these things go by the name TR groups. So this is TR K plus 1, Q of A at P. I'm not going to use that notation, but I just wanted to tie to the notation that Emanuele was using. So these are the TR groups that he was talking about on Monday. Okay, I need to not only compute these groups, but I also need to compute the restriction in the Frobenius maps, right, if I want to be able to take this limit. So this is sort of my goal if I want to do an algebraic K-theory calculation. Okay, so we'll keep the goal in mind. And there's one other thing I want to tell you about these homotopy groups, these fixed points of THH that we need to compute. So the one other thing to note, so there's also another operator floating around. So I have this F and R that we've already seen, but the Frobenius has an equivariant transfer. In other words, I get a map in the other direction. So I get a map V, which is going to go from the CP to the K minus 1 fixed points to the CP to the K fixed points. And this map is called the Verschiebung. Let's see if I can spell Verschiebung. Verschiebung. Okay. So this is my goal, is to try to understand, or well, this is a goal, is to try to understand these fixed points of topological Hochschild homology. They have all these operators on them. Depending on what kind of algebra you interact with frequently, some things about this may feel familiar. So, you know, there are other sort of algebraic objects where we see things like Frobenius, Verschiebung, and restriction maps. And I want to tell you about one of them. So we're going to put a pin in this. We're going to remember our discussion of THH, but we're going to step aside from it for a minute and do a little algebra detour and talk about Witt vectors. So what are Witt vectors? Well, Witt vectors are some algebraic object. They come up a lot in like algebraic geometry, number theory, also in topology. And so let's remember or learn what Witt vectors are. I want to think about Witt vectors for a commutative ring. So let's let A, for A, a commutative ring, P, a prime, let's pick an integer greater than or equal to 1. There is a ring. It is a ring of p-typical Witt vectors. That was, okay, wrong order. A ring of length k, p-typical Witt vectors on A, which we write like so, wk of A. And I want to tell you what this ring is ever so briefly. So the ring of p-typical Witt vectors on A, as a set, it is simple enough. So as a set, this thing just looks like a product of k copies of A. So my elements are just k tuples of elements of A. But it has this weird multiplication and addition on it. So to define the multiplication and addition, we need to define something else first. This is going to feel like a detour if you haven't seen this before, but it's just how it goes. So we need to define what's called the ghost map. So the ghost map is a map from the p-typical Witt vectors to my product of k copies of A. And I'm going to tell you where it takes A0 through AK minus 1. It maps it to these, we call them W0, WK minus 1. People call the coordinates on the left the Witt coordinates and the coordinates on the right the ghost coordinates. Okay, so I need to tell you what the ghost coordinates are. And the ghost coordinates are specified by the following formula. The ith ghost coordinate is A0 to the p to the ith power plus p A1 to the p to the I minus 1, and so on until at the end, what do we get? P to the I AI. Okay, so we have this ghost map. Okay, and what does the ghost map do for us? It turns out, and I'm not going to argue this for you, but it turns out you can prove that requiring the ghost map to be a natural transformation of functors from rings to rings, I'm just going to say a map of rings, requiring this to be a map of rings determines multiplication and addition on these p-typical Witt vectors. Okay, so that's sort of a weird way to define the multiplication and addition on a ring, but this is how it is for our Witt vectors. And you can try to write down some formulas like explicitly for what the multiplication and addition is, but it gets real fast, real bad, because the formulas are very complicated. But this is a way of characterizing what they are. Okay, so we have these Witt vectors. This is some ring that we associate to our commutative ring A. And if you've seen Witt vectors before, you may be familiar with the fact that Witt vectors come equipped with a number of operators. So for instance, I have an operator on the Witt vectors called R, which goes from the length k p-typical Witt vectors to the length k minus 1 p-typical Witt vectors, and people call this the restriction. I have an operator F, which goes from the length k p-typical Witt vectors to the length k minus 1, which is called the Frobenius. and I have an operator V, which goes in the other direction from the length k minus 1 to the length k, and this is called the Verschiebung. Oh, I spelled it wrong that time for sure. Verschiebung. There we go. I'm not going to define all these. It's sort of beside the point, but maybe just, I don't know, just to have one of them. So, for instance, the Verschiebung, if I take an element here, A0 through AK minus 2, this is maps to just putting a 0 in front. Okay. And we have descriptions of these other operators as well. And these operators, oh, it's a moment where I realized I forgot to say something, but these operators satisfy some relations. So plus relations, for instance, that if I do the Verschiebung followed by the Frobenius, I get multiplication by P. The thing that I forgot to say, which should have been right here, is that that's true for THH as well. So FV is equal to P in the THH setting as well. Okay, so now this all feels like perhaps very coincidental, right? Like certainly we see some parallels between the operators on the fixed points of THH and the operators on these Witt vectors, and that's not a coincidence. So this is a theorem of Hesselholt and Madsen, which Emanuele actually mentioned. Emanuele mentioned on Monday, but let me tell you what it says again. So they have this very nice theorem that says, so Hesselholt and Madsen proved that if we look at pi0 of the fixed points of THH, so if we're interested in understanding these fixed points of P to the K, here A is a commutative ring. They proved that this is actually isomorphic to the length k plus 1 p-typical Witt vectors on A. And that map is usually called lambda. Okay, so this is a very nice theorem. We're trying to understand these fixed points on THH, and Hesselholt and Madsen say, actually, for pi0, there's something familiar, something that has pre-existed and been around a lot, has a lot of applications. It's these Witt vectors. And this map, it respects all of these operators, so lambda r is r lambda, etc. And so Hesselholt and Madsen then went on and asked the following question, which is like, well, I understand what happens at pi0. Can I understand what happens above pi0? Like, so what is the algebraic structure of pi q of these fixed points of THH? And it turns out that they were able to answer that question as well. So they were able to really understand the algebraic structure in this setting as well. And to tell you their answer, I first have to tell you one more thing about the Witt vectors, which is that the Witt vectors have, oh, they're up there now, have these operators, R, F, and V. But the Witt vectors also have what we might call a multiplicative lift. There's a map from the ring to the, let's do length k plus 1 Witt vectors on A. And this map, I'm going to call it bracket sub k. And this map sends A to A sub k, which is just A 0, 0, 0, 0, 0, 0. Okay, if there are any Witt vector experts, and well, I know that there are Witt vector experts in the audience, but if anybody's following really closely, this is a choice, not a typo, to call this bracket sub k. Normally it would be bracket sub k plus 1 in the literature, but for the equivariant direction I'm going, I have to reindex things a little bit. Okay, so there's this multiplicative lift map, and Hesselholt and Madsen are after this question, what is the algebraic structure of the fixed points of THH? And they were able to characterize that structure. Emanuele mentioned this on Monday, actually. He said there's a thing called a Witt complex, which just is the algebraic structure of this. He didn't want to write it all down. I don't want to write it all down either, but like he made the right choice, except that I need it, so I had no choice. So I wrote it ahead of time, so I'm sorry if anybody's trying to take notes. I hate it when people do this, but I wrote it here, and just to emphasize that maybe we don't need every detail of this, but I want you to be able to look at it as we talk. So this is what Hesselholt and Madsen say. They say if we have an odd prime and A is Z-localized at P algebra, they define a Witt complex. It's a pro-differential graded ring that receives a map from the Witt vectors. We have a strict map of pro-graded rings F. We're supposed to think that's like our Frobenius from earlier. It commutes with lambda. We got this strange relation, FD lambda of the multiplicative lift. So we got some complicated relation in here as well. And then we have a strict map of E dot star modules V in the other direction. Lambda V is V lambda, FDV is D, and FV is P. Okay. I'm going to leave that up so we can look at it, but I'm also going to draw a picture. Maybe only a topologist would call this a picture. I'm going to draw a diagram. So let's try to just draw a little bit of like what's happening here so we can get a sense of what this data looks like. Okay, so in a Witt complex, I'm supposed to start with my Witt vectors. So I have like my length 1 p-typical Witt vectors, my length 2 p-typical Witt vectors, my length 3, and so on. And we said that the Witt vectors had these operators between them. There was R, there was F, there was V in the other direction. So I have this. And then in a Witt complex, my Witt vectors are supposed to map to level 0 of my my pro-differential graded ring. So this maps to E10, depends where I put the dot in the star. Oh no, I did it wrong, sorry. E10, E20, E30. These are my maps lambda. And in my Witt complex, I also have operators F and V. I'm going to put an R here, and you're going to complain because there's no R in the definition. But what is the R? Everything is a pro-differential graded ring, so the R is the pro direction. It's your structure map in your pro ring, just calling it R. Okay, it's a differential thing, so I've got a differential now that's going to take me to E1, 3, E12, E11. And then again, I have my operators there, etc. Oops. So we've got things going off in all of these directions. But this is the data of a Witt complex, is all this data, all this algebraic data, and these relations between them. And so what was Hesselholt and Madsen's theorem? Hesselholt and Madsen's big theorem is that, so theorem, Hesselholt and Madsen, is that for P, an odd prime, and A, Z localized at P algebra, what Hesselholt and Madsen showed is that the homotopy groups of fixed points of THH, let me make sure I get my indexing right, that if I take my E dot star to be pi star of THH of A, CP to the dot minus 1, that this is a Witt complex. So they completely characterized the algebraic structure of these fixed points of THH. And then Emmanuel, I mentioned this, but I want to make the point by reiterating that further, they also showed that this category of Witt complexes over A has an initial object. Initial object, which is the de Rham Witt complex. So the de Rham Witt complex already existed for FP algebras prior to this by work of like Bloch and Deligne and Illuzy. But Hesselholt and Madsen's approach allowed for a more general definition of the de Rham Witt complex over more rings. And it agrees, in the cases where it overlaps, agrees with the existing thing. So the initial object was some already kind of known and understood thing, the de Rham Witt complex. Okay, so this theorem is really nice from two perspectives. One, if you, like me, like to compute things, you probably know that the more rigid algebraic structure you have, like the better chance you have of being able to compute something. So this is like putting a really rigid algebraic structure on these things that we're trying to compute, these TR groups or fixed points at THH. The other thing is that, point 2 is that having the de Rham-Witt complex be the initial object means that these fixed points at THH, they always get a map from that initial object. So if you look at K-theory calculations, a lot of times you see the de Rham-Witt complex floating around. And this is one reason why, is because we have a map from the de Rham-Witt complex into fixed points of THH. Okay, so lost track of which board I'm on. Maybe we'll go here. Okay, that was the title of my talk was Topological Hochschild Homology, Witt Vectors, and Equivariance. And so we've done some THH, we've done some Witt Vectors. I mean, arguably, we've also done some equivariance, but I'm going to make things now more equivariant. So this story I've been telling you, this is kind of an old story. I want to tell you some new things now. So in recent years, there's been the development of several equivariant forms of THH. So I want to tell you, so THH is, of course, this is a confusing thing to say, because THH is, of course, itself equivariant. When I say equivariant THH, I mean THH that takes an equivariant input. We heard about one of them on Monday from Emanuele. Emanuele talked about real topological Hochschild homology. I don't think he actually called it that, but he was talking about this Z-mod 2 refinement of topological Hochschild homology. This is usually called THR. It's originally due to Hesselholt and Madsen also. There's twisted THH, which I'm going to tell you more about in a minute. This is written THHCN, and this comes out of work of Wiegleich Engeltveit, Andrew Blumberg, myself, Mike Hill, Tyler Lawson, and Mike Mandel. And I'll tell you what this is in a second. And then even more recently, there's some other new versions of topological Hochschild homology that take equivariant input. For instance, there's a quaternionic topological Hochschild homology, quaternionic THH, which is written THQ, and that's in very recent work of Gabriel Angelini-Knoll, Mona Merling, and Maximilian Peru. And they actually develop a whole family of new kinds of THH. This is just one example of something that appears in their work. Okay, so I'm going to focus today on twisted THH, but actually I think a lot of the ideas of what I'm saying in this project could be applied in these other settings. This is something that we're also thinking about. Maybe I'll mention that at the end. But I want to tell you a little bit about twisted THH. So what is this twisted THH? The construction of THH comes out of thinking about equivariant norms. So we've heard mentioned a lot this week the importance of Hill-Hopkins-Ravenel norms. So Hill-Hopkins and Ravenel, in their work on the covariant invariant 1 problem, developed these norm functors, which have seen many applications beyond that since then. And so just to remember, if we have G, a finite group, and H, a subgroup of G, Hill-Hopkins-Ravenel norm functors take us from H spectra to G spectra. We have this multiplicative norm. It lends itself very naturally to the question, though, like Hill-Hopkins and Ravenel's work is for finite groups. And so one could ask, like, what if your group's not finite? Can we take the norm to something not finite? And some of the first work in that direction is due to this collaboration with, I'm not writing all those names again, so Engeltveit, Blumberg, myself, Mike Hill, Tyler Lawson, and Mike Mandel. And there was related work around the same time due to Martin Stoltz. And what were we thinking about in this project? Well, we were thinking about, what does it mean to take a norm to S1? What does a norm to S1 look like here? And so in this work, we construct norms to S1 and show that actually topological Hochschild homology is the norm from the trivial group to S1 of R. So another way of saying that is that we show that the cyclic bar construction, that thing we saw earlier, it is a model for an equivariant norm. Okay, so topological Hochschild homology we could think of it as a norm. Once you take that perspective that THH is the norm from the trivial group to S1, you could naturally ask, well, can I norm up from other stuff to S1? Like S1 has other subgroups besides just the trivial group. And so we do that. And so in this same work, we say, yeah, you could norm up from something else. You could norm up from, like, let's say Cn, a cyclic group sitting inside S1, and you could define that thing to be a twisted version of topological Hochschild homology. Let's call that THH-Cn. And you know, to be clear, we construct it explicitly, so we construct a model for this norm, construct a model via a twisted cyclic bar construction, which I don't have time to tell you about today, but I'm happy to talk after if you want to know more about what that actually looks like. But we can define this twisted topological Hochschild homology. Maybe one note is that we also show in that same work that if P doesn't divide N, twisted THH is P cyclotomic. I haven't really told you what that means, but what was the point of cyclotomic? It was that you could define topological cyclic homology. So the takeaway from this is, so we can define twisted TC as well. So defined in that same work. Okay, so you might ask why you want to think about twisted THH. I'm going to tell you some things about twisted THH. So why should you be interested in twisted THH? I have two thoughts about that. One is that, you know, we're interested in equivariant norms. So twisted THH arises naturally from this perspective of the norms, and that's one reason to think about it as an object that we care about. But if you think about ordinary THH, why did we start caring about ordinary THH? I mean, I guess I don't know. I'm old, but not quite that old. So that was before my time when ordinary THH was being developed. But it was, you know, it was developed as part of a program to understand algebraic K-theory, right? It was developed to receive this map from algebraic K-theory as this approximation. So we could ask if something similar is true here, like what is THH-Cn related to? And I think that's an interesting question. So we're seeing that it has relationships. So I'm going to be vague here, but twisted THH is related to Merling's equivariant algebraic K-theory that we've heard about. Algebraic K-theory. And there's some work to that effect that's, I really have a tough time alphabetizing these names. Right, okay, that's work of Catherine Adamic, myself, Catherine Hess, Inbar Klang, and Hannah Gia-Kong. So we prove some relationship between Merling's equivariant algebraic K-theory and twisted THH, and then there's more work being done to develop trace methods for equivariant algebraic K-theory, in progress work of David Chan, myself, and Inbar Klang. Both, yeah, a lot of these people either are around or will be around this semester. Okay, so I should tell you about the project that I actually promised to talk about. So what is the question that I want to talk about? So Hesselholt and Madsen were able to understand this rigid algebraic structure of fixed points of THH. And now we have these new versions of equivariant THH that we'd like to understand, interesting as norms, also in sort of a trace methods perspective. And so I'd like to ask the same question. What is the algebraic structure of fixed points of twisted THH? Okay, so I want to try to bring that question to this new setting and see what we can figure out. Okay, we've learned this week, we've talked a lot about how equivariant homotopy theory has its own kind of algebra that comes up, right? You know, we get these tools like Mackey functors that arise from the equivariant setting. And people often call that equivariant algebra, the kind of algebra that we get here. So, so let's think about, we're going to need some equivariant algebra to answer this question. So Clover gave us this super helpful dictionary on Monday about how to think about equivariant algebra and ordinary algebra. So I'm going to rewrite Clover's little translation. So I want to think about algebra versus equivariant algebra. And one of the slogans throughout the whole week has been the following, that I care in algebra about and topology about abelian groups. And we've learned that the abelian groups of equivariant homotopy theory are Mackey functors. So here I should have Mackey functors. Okay, Clover gave us a beautiful definition and introduction to Mackey functors, so I'm not going to define them again, but let's just remember that they're the abelian groups of equivariant homotopy theory. So in particular, if I have X, a G spectrum, I get a homotopy Mackey functor for X, where when I evaluate it on an orbit, I get homotopy Mackey functors. Sorry, when I evaluate it on the orbit, it's homotopy groups of fixed points. Okay, this is some sense in which I'm supposed to think of Mackey functors as abelian groups, is that G spectra give me now homotopy Mackey functors. Okay, Clover also mentioned that, in algebra, maybe I care about rings. And there's an analog equivariantly called green functors. So we haven't gone into this in too much depth, but this category of Mackey functors has a symmetric monoidal product. You can look at monoids and you get green functors. And then several people have talked about how if you're interested in commutative rings, though, you need something more. You really want to take what are called Timbara functors, which are sort of like these green functors, but we have the addition of what we call internal norms. Okay, so this is our dictionary as we have it so far, and what do I want to do? Well, I want to make a big jump from commutative rings all the way to Witt complexes. So, I want to now generalize that to equivariant, the equivariant setting, and so we might wonder, like, what do we put here? And then you think, oh, that seems ambitious, right? Because the pieces of this maybe aren't even on my chart yet. So what's the first piece that you would need? If I want to understand a Witt complex, surely first I should understand the Witt vectors. That seems maybe like a better place to start. So let us do that. Let's try to understand Witt vectors in this setting. So it turns out that you can do. So that's work of Blomberg, myself, Mike Hill, and Tyler Lawson. We thought about Witt vectors in this equivariant setting. And so what did we do let's see. Let's say we defined equivariant Witt vectors for green functors. So green functors are analog of rings, so we define a notion of Witt vectors for green functors. And what do we prove with that? Well, the theorem, a theorem about these Witt vectors is that if we have a Cn Timbara functor, R, and let's say that I'm interested in the Cn twisted topological Hochschild homology of R, and I want to take its equivariant homotopy. So I'm going to take equivariant pi 0, Ckn. We prove that this is isomorphic to the equivariant Witt vectors of R. So how should you think about what that is saying to you? What that is saying is that this is exactly analogous to Hesselholt-Madsen's theorem about pi 0 of the fixed points of CHH being the p-typical Witt vectors. Now you don't see the fixed points over, also doesn't make sense what I wrote. You don't see the fixed points over here because they're now hidden in the Mackey functor. Remember, this Mackey functor is homotopy groups of fixed points. So maybe it looks different than Hesselholt-Madsen's result, but we could rewrite Hesselholt-Madsen's result in a more Mackey functor way if we felt so inclined, and then you would see the parallel more directly. But this is exactly what Hesselholt-Madsen were telling us, that pi 0 of fixed points of THH, now twisted THH, is captured by the Witt vectors. Okay, so that seems promising in terms of being able to, so this is, okay, we do have a way of thinking about Witt vectors in the equivariant algebraic setting. And so now we want to think about a Witt complex. So the question becomes, what is the algebraic structure above degree 0? So, question is, what is the algebraic structure of this thing, pi q of GH of R for all q greater than or equal to 0. I'm being a little vague about what group I'm taking equivariant homotopy with respect to, but this is the question that we want to ask. Okay, and now everything I'm going to say in this last bit is joint with Anna Marie Bowman, Cameron Kralewski, Sarah Peterson, and Lucy Yang, where we try to answer this question. What is an equivariant Witt complex? What is this equivariant? What is this algebraic structure? So one always hopes, or maybe it's just me, but I feel like one feels so hopeful with these equivariant algebra projects that like, oh, maybe everything just translates real directly and it's all going to be super smooth and I'm just going to like figure out the equivariant. Yeah, Mike says he feels the same way, so then I feel justified. But then it turns out that like, you know, as is often the case, everything turns out a little bit more difficult than expected. And one way you can see in this project, like where things immediately become a little bit more challenging is like, to think about Hesselholt-Madsen's Witt complex, I had that map, that multiplicative lift map from A to the vectors on A, and k plus 1. And this map was just like, it was just A goes to A. It was so nice, right? Just like it was such a nice map. This doesn't make sense for us in the equivariant setting, in part because in this work with Blumberg and Hill and Lawson, we defined these Witt vectors in a very different way than they're defined classically. They have the properties that they want. They behave like we want, but they're not defined as like a product of, like you might guess a definition and that's not the definition, that's not how they're defined. And so this doesn't make sense to talk about like this, or we don't know how to do this like this. So step one was that, you know, in this work, we had to define an equivariant multiplicative lifts using very different methods than in the non-equivariant case. And so let me just, I'm not going to tell you the definition, but I'm going to write down the form of the map just so you can see what it looks like. So we have R Cn Tambara functor, R Cn Tambara, and our maps now look like maps from R. I have to get a map for every orbit, Cn mod Cm, maps to this Cp to the Kn equivariant Witt vectors on R at the orbit Cp to the Kn mod Cp to the Km. And as opposed to this very like element-wise, coordinate-wise description of the multiplicative lift non-equivariantly, we have to do something more complicated here using the internal norms in Tambara functors. So whenever you take a real like sharp turn from what happens classically, you have to always ask yourself, how do you know that you've done the right thing, right? Like, how do you know that this is the multiplicative lift that we were actually looking for? And so there needs to be some justification for that. The non-equivariantly, this multiplicative lift lifts the p to the kth power map. That's a nice thing about it. And so we prove that equivariantly that's true as well. So proposition I like know who all the people are. I'm really alphabetizing. Yeah. Anyway, sorry. What did we prove? We proved that this equivariant multiplicative lift, lifts the p to the kth power map. Okay, so what do we go on to prove? So what were we trying to do? We were trying to define an equivariant Witt complex, and I'm gonna, for the sake of us all, I'm not gonna write down in excruciating detail what the definition is. I'm just gonna bullet point it for you, because there are a lot of details. But what does this thing look like? So I'm gonna put definition in quotes. And we're going to look up at Hesselholt-Madsen. We left this up here so that we can sort of see the parallels and the not parallels between them. And so what is my definition? So our setup now is that for p naught prime, an odd prime that doesn't divide n. I've got R, a Cn Tambara functor that is a Z localized at P algebra at each level. And we define a Cn, we define a Cn equivariant Witt complex over R. Okay, and I'll bullet point it for you in a second, but let me tell you what the theorem is before we do that. So we define our Cn equivariant Witt complex, and then our theorem is that it captures the structure of the equivariant homotopy of twisted THH. So theorem, Bowman, Gerhardt, Kralewski, Peterson, Yang, is that the equivariant homotopy of twisted THH is one of these equivariant Witt complexes. So is an equivariant Witt complex. Okay, so another sort of result that you would want, which we also proved but I won't write down, is that you'd want to know that when n equals 1, that you recover Hesse-Holt-Madsen's ordinary Witt complex, that this is a true equivariant generalization, and that's true. When n equals 1, you can get back Hesse-Holt-Madsen's Witt complex from this. But let me tell you a couple things about what this looks like, and then we'll stop. So what is this thing? It's a collection of graded green functors, so Cp to the Sn, graded green functors. They have to be compatible in some sense, but I'm going to write them as E star Cp to the Sn for all s greater than or equal to 0. So I have this collection of graded green functors. I have differentials at each level of my green functors at each level. I have a map from the Witt vectors, so a map lambda from the equivariant Witt vectors. I have, and then plus relations. A lot of the relations are about how the lambda interacts with the R and the F and the V. I'm not going to write all those, but the relations include FV equals P, FDV equals D, and then this complicated one that we had now is with our multiplicative lifts, but the same complicated relation that we had in the non-equivariant setting we have here as well. You have to put some restriction here if you really trace it through to make this make sense. You need some restriction there, but we have this complicated relation here as well. Now, I got 1 minute to say that, you know, if you compare here to here, and then if you stare at this too long, you might feel like confused or angry. I don't know, it depends on how you run, I guess. But the, but like this doesn't like Hesse-Holt-Madsen, all their structure was about the F and the V, right? And there's no F and V in my bullet points, but yet there is an F and V in my relations. So it feels like clearly I've done something suspect. So what have I done? Well, the F and the V, we get them for free because it turns out that Frobenius and Verschiebung, they were secretly all along like the restriction and transfer in a Mackey functor. And so we do have the F and V. I'm just using F and V as notation here. For V is transfers in these Mackey functors, and the F, in a really unfortunate clash of notation in this field, the F is the restriction in the Mackey functor. It's not the same thing we were calling restriction earlier, so I don't know. This one's not my fault, but the F and the V's are here. They're in this graded green functor. Okay, so we produced this equivariant Witt complex, and we proved that it captures the structure that we wanted in twisted THH. And then just the last thing I'll say is what we're doing now and sort of our future directions. So one direction that we are interested in is that there should be a real story, like a THR story like this as well. So we're working on developing a notion of a real Witt complex. The Witt vector piece of it, Witt vectors for rings with anti-involution, that exists in the literature already, and we're working on developing the Witt complex aspect of that. And then the other most natural question after seeing this, maybe people already maybe have this question in their mind, is like, Madsen defined a Witt complex, and then they studied the category of Witt complexes. It had this initial object, which was a de Rham Witt complex, which is a super useful thing. And so do you get from this some equivariant de Rham Witt complex? And so that's something that Anna Marie and Sarah and I have been talking about just last week a lot, but thinking about what the equivariant de Rham Witt complex looks like in this setting. So, 38 seconds in the red, so I'll stop.
Thank you very much. Do we have some more questions?
Can you give us some idea how this looks like, say, for the constant FP tomorrow factor?
Like the whole thing?
Something.
No, no. We do calculations of no, it's gone now. But like in the stuff where the Witt vectors are originally defined, there's not like a lot of computational stuff. And so in this paper, we do some explicit calculations just of the Witt vector piece, and I couldn't reproduce them off the top of my head in the constant FP case. But you can see, I mean, like for the Burnside-Mackey functor or something, it's very nice. These Witt vectors are defined actually using Hochschild homology for green functors. And so like if you take the G equivariant Witt vectors on the H equivariant Burnside-Mackey functor, where H is a subgroup of G, it just spits out the G Burnside. So this is sort of a trivial case. But you're gonna get, but the Witt vectors are going to look like, anytime you have a Mackey functor where the Weil actions are trivial, the Witt vector piece of it is, let's say a Tamara functor where the actions are trivial. The Witt vector piece of it is just going to look like a norm from whatever group, like a Mackey functor norm from whatever group you started with up to the group that you take equivariance with respect to. So that's what the Witt vector piece looks like. We haven't done explicit, I mean, we've done explicit calculations of that and explicit calculations of like the multiplicative lift maps, but we haven't written down like real explicit calculations yet of the whole Witt complex. Yeah. We should.
So this is a description of THH of R as norming up from the trivial group to S1 of just R itself.
Mm-hmm.
And from that we proceeded with like considering norming up from some other subgroups of S1 to S1.
Yeah.
Does there also, like, is there also interesting cases of norming up from the trivial groups to some other group that is not S1?
Oh, yeah. So, right. If we want to take norms up to other not finite groups that are not S1, here's some things I can tell you. So you can also think of real topological Hochschild homology as a norm. So that one's a norm from C2 to O2. So that's a different, that's a confusing point at first, as people often think maybe C2 twisted THH is the same as THR. Those are two different things. It's easy to see that from the norm perspective. There's work of Andrew Blumberg and Mike Hill and Mike Mandel about norms to compact Lie groups in general. And so they have some work on that where they show that their definition recovers, like for S1 recovers the stuff that we had done previously. So there are people thinking about that as well. And then I think I mentioned these new theories of THH due to like Maximilian and Mona and Gabe Angelini Knoll. And I think those two we should think of as equivariant norms. Like I think this quaternionic THH morally is like the norm from C4 to pin 2. Sorry, looking at Mona and Maximilian. C4 to pin 2 of twisted C4 ring. And so, yeah, so there are these other instances where we understand it in this concrete way, and then Blumberg, Hill, Mandel have like a more abstract program to understand norms for compact Lie groups.
Another question in the back?
Yeah, Natalie?
Perhaps maybe I should be asking this to Blumberg, Mandel, or Hill, but are these norms related to equivariant factorization homology?
So that is what they do. I mean, yeah, you should ask Mike, but I'm going to answer and then Mike's going to correct me. But I think yes, because their work on developing the equivariant norms for compact Lie groups, part of that is developing a new framework for equivariant factorization homology that works with these norms. Did I just say a correct thing?
Yeah.
Okay. Mike approves. Yeah, Jeremy.
So classically, if you have like a perfect field, TR of it is the Witt vectors in the sense that TR of it is discrete, which is kind of easy.
Yeah.
Do you have any idea if there's some things for some analog of this discreteness or certain?
Yeah, that's a great question. I haven't thought about that, so I don't know. That's a very good question, though. I don't know in this equivariant setting or not. Yeah, I gotta think about that.
One more? Yeah.
Is there a generalization of the kind of vector story for like non-discrete rings, or is it only for?
Sorry, say
Is there
again?
a generalization for non-discrete rings, like just ring spectra in general, or is it only for?
Oh, for like twisted THH and stuff?
Yeah.
Yeah, I mean, all this stuff is defined. Well, okay, yeah. I was focusing on thinking about, here. Right, so yes, in terms of the relationship to the Witt vectors. So for the relationship to the Witt vectors, both here and in Hesse-Holt-Madsen, like I could have here instead put like R, a commutative CN ring spectrum, and then here I'd put pi 0 of R, and this thing would be true for at the level there, and that's true of Hesse-Holt-Madsen's theorem as well. I stated their purely algebraic version, but they have a version too that says that you can do this at the level of ring spectra. For the Witt complex, no, that's really, we're thinking about that just for, we need at the level of like taking a Tambara functor as input.
All right. No further questions. Then we have a lunch break, and then there's one more.